Okay guys, today we're going to learn about inverse functions. Now before we learn about inverse functions, what we have to understand is something called a one-to-one function. And the definition of a one-to-one function is the basic definition of a function, which is every x has only one y, right? That's the basic definition of a function. But we add on to it the fact that every y also has only one x. So if we look at this example of a normal function, f of x equals 2x, we can see that 1 maps to 2, 2 maps to 4, 3 maps to 6. This is a one-to-one function, right? Because every y has only one x, and every x has only one y. Now if we look at this function, okay, this is a 1 maps to 8, 2 maps to 12, 3 also maps to 12. Now this is a function. This is a function because every x has only one y, but this is not a one-to-one function because, well, 8 maps to 1, that's okay, but 12 maps to 2 different numbers. So this is not a one-to-one function. Now the rule about one-to-one functions is every one-to-one function has an inverse function. And an inverse function is just a function that goes backwards. So in this first example, if I have f of x equals 2x, then my inverse function of f of x, we would write that as f prime, or negative 1 of x, is going to equal 1/2 x. And we can see here, if I wanted to go backwards, I can plug 2 into here. 2 times 1/2 is 1. That clearly maps back to 1, right? If I plug 4 into here, 4 times 1/2 is 2. That maps back to 2. If I plug 6 into here, 6 times 1/2 is 3. That maps back to 3. So that's the definition of an inverse function. Okay, so guys, that brings us to properties of inverse functions. And there are 2 basic properties. If f is a one-to-one function, all one-to-one functions are going to have an inverse function. So f is going to have an inverse function f of negative 1. And the other property, of course, is if b equals f of a, then the inverse function, we could just flip the b and the a. Right? So a would equal f of negative 1 of b. So in this case, if I were to say 2 equals f of 1, then on the inverse side, we would say 1 would equal f of negative 1, 2. Right? By plugging in the 2 into the inverse function, I would go back to the original input, which is 1. Let's take a look at an example. For function f of x equals 3x plus 1, find the inverse function f of negative 1x. So in this case, what we're going to try and find is a function in the same form using x, but we're going to flip it. And what I mean by that is, let's turn this f of x into a y for now. Y equals 3x plus 1. And to find the inverse function, what I'm going to do is I'm going to swap all of the x's and the y's and then solve for y again. So in this case, x equals 3y plus 1. Okay, and then I'm going to solve for y. I put y by himself. So subtract over, x minus 1 equals 3y. Y would equal x over 3 minus 1. So this is the inverse function. This is the inverse function f of negative 1, x equals x over 3 minus 1 over 3. That's my inverse function. And we can do a quick check. If I plug in, say for example, the number 0, let's do a little xy table for the original function, f of x. This is f of x. If I plug in 0, what am I going to get? I'm going to get 1. Right? If I plug in 1, what am I going to get? I'll get 4. And if I plug in 2, what would I get? 2 times 3 is 6, plus 1 is 7. Now let's double check and see if the inverse function goes the opposite direction. So if I plug in 1 into here, what do I get? If I get 1/3 minus 1/3, that's 0. Right? That takes me to here. If I plug in 4 over here, 4 over 3 minus 1/3 is 3 over 3, which is 1, which is exactly that. If I plug in 7 over here, 7 over 3 minus 1 over 3 is 6 over 3, which is 2. So clearly this is the inverse function of that. Okay, now let's take a look at graphs of inverse functions. There's a couple of properties we want to note about graphs of inverse functions. One is that any point BA on the graph of f of -1 is the reflection of the point AB, okay, on the graph of f. The graph of the inverse function of f is a reflection of the graph of f across the line y equals x. So remember, the line y equals x is the diagonal line at 45 degrees across the origin. So basically what it's saying is any point along the original function of the graph is going to be reflected across this line to the other side of the line. Let's take a look at an example. So for function f of x equals 3x plus 1, that's the function we were looking at in the last example. Let's take a look at the domain 0 less than or equal to x less than or equal to 2. So 0 to 2. We want to sketch the graph of f, also f of -1, and state the domain and range of both. So over here, what I've done already is sketch the graph for f of x from 0 to 2. So I plugged in a few points. I know at 0, 0 times 3 is 0, plus 1 is 1, so I got 0, 1. I know at x equals 1, we have y equals 4. And at x equals 2, y equals 7. Now the next piece is the inverse function. And according to this property, any point AB on the original graph, we just flip them. We just swap the points, right? So if this is 0, 1, then I know on the inverse function, I'm going to be at 1, 0, right? I know that for this guy, 1, 4, let's just swap it again. Let's go to 4, 1. And for this last one, 2, 7, swap it again. Let's go to 7 and up 2. And here is my inverse function. Now note that this line is, like we said, directly reflected across y equals x. Right? This line is y equals x. This line is directly reflected across y equals x to the other side. And that's always going to be true for inverse functions. They're always going to be reflected across y equals x. The domain of f of x we've already stated up here, 0 until 2. The range, well, the range goes from all the way from 1 up to 7. Now the domain of the inverse function is actually just going to be the exact opposite of f of x, right? It goes from 1 until 7 on the x-axis. And the range goes from 0 until 2, which is the exact opposite of the domain. There we have it. Okay, guys, so for the last topic, what we're going to look at is inverse composite functions. And inverse composite functions, there's just one property we need to remember, and that is the inverse function of the function gf is going to be, of course, the inverse of gf. But we can also express that as the inverse of f of the inverse of g. Now, a quick thing to note, when we do it this way and we take the inverse of each individual function, we actually reverse the order. So here we have gf and then the inverse. Here we have the inverse of f and then the inverse of g on the inside. So it's important to note. Let's take a look at an example and I'll prove to you that this is true. We have two functions, f of x equals 1 plus 3 over x, and g of x, which equals 2x. And we're going to find all these things. Let's start with finding the inverse of f. So in order to do that, of course, we set up the original function, and then we just swap the x's and y's, right? So here's the original function. We'll swap the x's and y's, so we end up with x equals 1 plus 3 over y. And let's continue solving for y here. So x minus 1 equals 3 over y. We'll have y equals 3 over x minus 1. So my inverse of function f is going to equal 3 over x minus 1. Let's find the inverse of function g now. The inverse of function g, let's set up function g first. That one's pretty easy. Y equals 2x. Again, let's swap our y's and our x's. So here we're going to have x equals 2y. Solve for y, we'll end up with y equals 1/2 x. So the inverse function of g is 1/2 x. Now let's look at gf. Gf is our composite function. So we're going to put f inside of g. So that means 2 times 1 plus 3 over x. That means we have 2 plus 6 over x. Oops. That's going to be my composite function for g of f of x. Plus 6 over x. Now let's look at the inverse of this function we just came up with. So again, setting up the original function, y equals 2 plus 6 over x, swapping our y and our x, and solving for y again. So we get x equals 2 plus 6 over y. We end up with x minus 2 equals 6 over y, and that means y equals 6 over x minus 2. Therefore, the inverse of the composite function gf equals 6 over x minus 2. Now, quick check, I want to prove that this piece is equal to each of the individual inverses put together. So what I'm going to do is create a new composite function using the two inverse functions that I found in B and A. So G is going to be on the inside, so we'll take this guy and plug him into that, and hopefully we get this. So 3 over 1/2 x minus 1 is going to equal my y for now. And I'm going to solve or simplify y equals 3 over x over 2 minus 2 over 2, which is going to equal 3 over x minus 2 over 2. Let's flip and multiply, which equals 6 over x minus 2. So again, f inverse of g inverse of x, I suppose I should put brackets around this, is going to equal 6 over x minus 2, which is exactly the same as what we found in the composite function and then finding the inverse. Okay guys, here's your practice problem for tonight. A one-to-one function f of x equals x squared minus 2x over the domain 1 to 3. Sketch the graph of both f and the inverse of x, and the inverse of f, and state the domain and range of both function f and the inverse function. All right, I'll see you guys tomorrow.